Welcome once again. My name is Joelle Larson. I'm the Director of Alumni Relations for the College of Science and Engineering, and I'm delighted to welcome you to this webinar featuring the U of M Solar Vehicle Project. I think you're going to find the presentation really inspiring. The students are doing amazing work despite the challenges of the pandemic and have found a lot of recent success. I'll turn things over to CSC Alumni Board Member Tom Jensen to welcome everyone.
Hello, and welcome to the University of Minnesota's College of Science Engineering webinar today. And today we get a chance to see the University of Minnesota's Solar Vehicle Project. The name of this one is Racing on the Sun, how the University of Minnesota's Solar Vehicle Project is driving technologies. My name is Tom Jensen. I'm with the University of Minnesota Alumni Board, and we enjoy webinars such as these today, where we bring work and academia together. So we look forward to having you enjoy it. You're going to get a chance to join the students from the University of Minnesota Solar Vehicle Project to learn how they use the latest technologies in the design, build, and race their solar vehicle cars. The team has raced on 3 continents and has most recently placed first in the Formula Sun Grand Prix and second in the American Solar Challenge. So join me and enjoy this. I would also encourage you to take a look at their webpage, where you get a chance to meet the team of the students and their leadership. And most interesting, go to the sponsors and take a look at the renowned sponsors, both local and nationwide, who help sponsor this exciting project. So for myself, as a father of 2 Golden Gophers, my son and my daughter both graduated from the University of Minnesota, and I'm a proud engineer with that pedigree as well. So enjoy the seminar today. We look forward to having you return again and again for these informative webinars. Thanks.
Thanks so much, Tom. And with that, let's get to the meat of the presentation. I'm going to start by turning things over to Brett from the Solar Vehicle Project. Go ahead and take it away, Brett.
Yeah, so thank you everyone for joining us today and taking the time to hear about the Solar Vehicle Project. We're very excited to share with all of you what it is that we've been working on. So we're just going to start with a quick introduction of each of us. So my name is Brett Duncan. I'm majoring in computer engineering. I joined the team in the fall of 2018 as the team's director of engineering from May of 2020 until September of 2021. I attended the 2019 Bridgestone World Solar Challenge, as well as the 2021 American Solar Challenge.
Hey guys, I'm Matt Ryla. I'm a sophomore majoring in computer science. I joined the team summer of 2021. I currently serve as the team's safety manager, and then I also am involved with writing firmware for the car. And I'm also involved with our composite layups process on the St. Paul campus.
Yeah, so to give you an idea of what we're going to talk about today, give you an overview of the team, talk about the race, the structure of the team, our design and build cycle, and then give you some insight into our current projects as well as our sponsors.
So I think we'll start with giving you guys kind of an overview of our team. We kind of live by our mission statement to create better engineers, business people, and leaders by providing students with hands-on experience while innovating solar vehicle technology. So we take some pride in saying that we are a student-led organization. All of the engineering and leadership is done by students, while we do have one faculty advisor. Yeah, all of our leadership is like student-led. So yeah, that's a great part of our organization. Just to give you guys some history of the team, we were founded in 1990 by a group of students. We first raced in the General Motors Sun Race in 1993, and we were the first team to drive a solar car across an international border during a race, which was into Canada. In our past, we have built 14 cars, and we are currently working on our 15th car. The 3 main competitions that we race in are the Formula Sun Grand Prix, the American Solar Challenge, and the Bridgestone World Solar Challenge, which is in Australia. And then here's sort of the demographics of our team. You'll see on the left all the different majors represented on our team. So Looks like our largest major is mechanical engineering. However, half of our team about is computer engineering, electrical engineering, or computer science. But we do have a good mix of majors across CSE and other colleges as well. And then on the right, you'll see the years in school of our team. So we do have a good mix, which is also, again, like what we like to see.
Yeah, so to talk about our races, the first race I'll talk about is the American Solar Challenge, which we refer to as ASC. So ASC happens in the sum of even years usually, although it also happened this past year because of COVID delays in 2020. And this race is really interesting challenge to us because it's a different route each time. So while it is in the United States, geography across the country varies dramatically. So sort of just the requirements and the design for the car has to change to accommodate that. And this race, with the route changing each time, is usually between 1,500 and 2,000 miles, and then somewhere between 5 and 8 days long. So this is a race on public roads for endurance over multiple days. And then on the right here, we have EOS 2 racing in the American Solar Challenge in 2018. So the Formula Sun Grand Prix is a track race, and so actually the only track race that we race in. This race happens every summer, and during even years it acts as the qualifier for the American Solar Challenge. So what that means is that you either need to get a minimum number of laps on one day or some larger minimum number over multiple days in order to qualify for the road race. This is just to make sure that teams have a roadworthy car that's capable of driving those thousands of miles that they will need to. So recently, we're only attending on years that ASC happens, but we've won this race 6 times, which is more than any other team, and that's something we're pretty proud of. Then this is Centaurus 3 during the 2011 FSGP. Then finally, the third race that we race in is the Bridgestone World Solar Challenge. This is really the premier solar car race. So this takes place during the fall of odd years in October. And then it's always the same route. It's in Australia. It's 3,021 kilometers from Darwin in the Northern Territory along the coast to Adelaide in Southern Australia, which is along the southern coast. So this is a bit of a different design challenge, very, very harsh conditions, but the conditions are also a bit more known since it's always the same route. And we'll have experienced members from previous races usually go along and give guidance to the younger members so that we have a better idea of what we're doing. And this is a pretty big commitment for team members who go to this race. Team travels there for a little over a month, usually leaving in mid-September and then coming back in October after the race is complete. And then on the right here, we have EOS 2 at the starting line for the Bridgestone World Solar Challenge in 2019. So these races have 2 different vehicle classes, so we'll talk briefly about those. So the first class is the single occupant vehicle class. And as the name says, the cars only have a single occupant who's the driver. And these cars are built for speed and efficiently. And we've built 10 of these. We no longer build these, but we built these for the majority of the time the team's been in existence. So to give you a look at some of our past cars, we have the 4 Aurora series cars, Aurora 1 through 4, left to right. As you can see, from Aurora 1 to then the later 3, the design changed quite a bit. And then we have the Borealis series, where the design changed some from the Aurora series, but among these 3 cars, the design is similar. And then we have Centaurus, built 3 of these, and Centaurus 3 most recently raced in ASC 2014. But what we currently race in is called the multi-occupant vehicle class. So these vehicles have 2 to 4 occupants. And while we're still trying to make an efficient car that can make the best use of solar power possible, we also keep real-world practicality in mind and try to build a car that's much more similar to what a commercial EV that you might go out and purchase would be. And the reason for this is that practicality is a scoring multiplier in this race. And unlike the single occupant vehicle class, where the race is much more like a race that you'd expect of the first car to cross the finish line wins, The base scoring formula is the number of people you have in your car times the distance you carry them divided by the energy used from the grid. So in this class, you can charge using a standard AC EV charger that counts against you. So you're incentivized not to do that, but you might need to be able to complete the race. And we've been competing in this class since 2013. That's when this class was first created at the Bridgestone World Solar Challenge. And the main reason we switched to this is we just wanted to really just be pushing the envelope in terms of technology and building cars that are not just not just a fast car, but also a car that is going to be more practical and more similar to an EV that you might one day buy. So the first car we built for this class was Daedalus, and this car only raced in the Bridgestone World Solar Challenge in 2015, and it placed fourth, which we did quite well. And not only was this our first car in the class, but it was also the first American-made multi-occupant vehicle, so that's something we're pretty proud of. And we built this car really quickly. We built it in less than a year. Usually it takes longer than that to build it, but the group of people who built this car were really motivated to get it done and get it to Australia and compete in that race. Then after Daedalus, we have EOS 1 and EOS 2. EOS 1 raced for the first time in World Solar Challenge in 2015, and then EOS 2 raced for the first time in 2017. As you can see, they both pretty similar design, but EOS 2 took a lot of what the team learned from building and racing EOS 1 and worked to improve and iterate on that. Then most recently, we have Freya, and Freya is our first 4-occupant vehicle. It's also the first American 4-occupant vehicle to race in the American Solar Challenge. So we raced it this past summer in the American Solar Challenge and got second place. And then we'll race it again this summer, hoping to win, working on making some improvements to it right now that we're pretty excited about. So to give you an idea of what race is like day to day, so we get up in the morning. We really want to maximize the amount of solar power that we get. So we get up before sunrise and get the car ready to charge. We normalize the array panel, so we point the array panels towards the sun as it comes up, just to maximize the amount of solar power we get. Every little bit helps. Not only is it power that we might need to be able to complete the next stage of the race, but it's also the more power that you can get from the sun, the less power that we might need to get from the grid later on. So that helps boost our score. And then for most of the race, we're camping either at a campsite or in Australia, you can actually just camp along the race route. And then we'll eat breakfast and get ready to drive. So people will get into their assigned vehicles and then do all sorts of procedural checks to make sure the car is in working order and ready to drive on the road. Once we start driving, the driving time is usually around 8 hours. Usually there's some sort of break in the middle of the day with either some sort of checkpoint. And then the driving speed depends on multiple factors. Of course, we need to follow the speed limit because this is a race on public roads. But primarily it's weather and geography that are going to determine how fast we drive on any given day. Weather such as wind or clouds is going to affect how much energy we need to drive or how much energy we're going to get from the sun. So the strategy team is going to look at that to make a decision on how fast we want to go. And then things like geography, especially elevation changes, are going to affect the performance of the vehicle. And things like motors, we might be concerned about the thermals on those. So we might drive slower or change our strategy a little bit. It's a day with a lot of hills. And then the solar car drives in a caravan, so it has a lead and a chase vehicle, and this is for safety. Solar car is like an experimental vehicle and student made. It doesn't have advanced safety systems like any commercial car you might buy. So we do that. And then we also have a scout vehicle that drives much further ahead to give us an idea of road conditions, as well as look for changing weather conditions that we might not know about. That's especially important in the World Solar Challenge when communications and internet are more limited. So having that is super helpful to us. And then throughout the race day, we might hit a checkpoint or a stage stop. So these are mandatory stops during the race that all teams are required to stop at. Checkpoints, depending on the race, are either 30 to 45 minutes long. And this is just an opportunity to make all teams stop, give the drivers a break from driving, let people switch out of the cars. And this is really mainly for safety, just to make sure that people aren't trying to push themselves too hard all day by driving without stopping because they don't want to lose that little bit of time. So these are just there for safety. And then stage stops, end racing for the day, and then the next stage would begin the next morning. And then on the right here was a checkpoint during this past American Solo Challenge during the second stage in La Junta, Colorado. And we were pretty excited when we got there. We were actually the first team to get there. And we were somewhere between 150 and 200 miles ahead of all of the other teams. We managed to get in front of a rainstorm, and we had sun almost the entire time while other teams got stuck farther behind. So we were pretty excited to get there. And then finally, during sunset, we want to maximize the amount of power we can get before the sun goes down. So once again, we normalize those solar panels to get as much charge as we can. We set up camp for the night and eat dinner. And then at night, we have the option to use level 2 AC charger. During the World Solar Challenge, this is more limited. You can't do that every night. You can only do it at 2 different points during the race. But on the American Solar Challenge, we have the option to charge nightly. But it's metered, so it counts against us. So we try to do that as little as possible. And then we'll take a look at the car, see if there's anything that needs to be repaired. Usually we'll change tires. And then of course, after a long day of race, we will try to get some sleep so that we can get up and do it again tomorrow.
All right, now sort of going into the structure of our team and like how we're laid out. We have 2, I guess, main parts of the team. We have our operation side of things, and then we have our engineering side, which has further divided into 4 sub teams there. So I guess first going into what our operations team does, they kind of handle all of the business stuff on the team. So the finance, the organizing different events, talking to sponsors, social media and marketing, and then as well as race logistics. So a lot of the communication, a lot of the business. They also do our merch design and also just making sure that we have everything that we need on the electrical side or engineering side. So the first sub team that we'll go over with the engineering side of things is the array. So they do everything with the solar panels. They design the solar cell layout for the car. They source and purchase the raw solar cells that we'll be putting on top of the cars. They solder the individual cells in series to create these modules. They do encapsulation at 3M, and then they repair any of the damaged cells if they're broken during the race. And here you can see EOS2 during the Bridgestone World Solar Challenge in 2019. The next sub team we'll go over is composites and structures. So they kind of do the aerodynamics of the car, which is a huge factor considering we have limited power. We need to maximize the output that we get. So a lot of that is minimizing the drag. They do a lot with the chassis design, roll cage, battery design, doors, and then the airflow throughout the cabin. And this is our most recent car, Freya, which was built last summer. Here you can see sort of the aerodynamic body design. This is kind of the first step in designing what the next car will look like. And it's the first system that we want to lock in place to design everything else around it. So it's kind of a highly iterative design process with kind of lots of changes being made to make sure it's the car that we want it to be. And we currently use Altair Virtual Wind to test the aerodynamics of the car. And we've previously used ANSYS to do this as well, which we still use for our mechanical side as well. Another system that we work on for CNS is the chassis, which is constructed using 1/2-inch thick carbon fiberglass and fiberglass panels. These are cut by a jet edge using a 5-axis water jet. And these panels are adhered using DP 460NS from 3M. So this is sort of what gives the car its rigidity and structure, as well as kind of being a point where we can mount all of our other mechanical systems on. So think of it like the skeleton of our car, more or less. And then next we have the roll cage, which is required by American Solar Challenge regulations. And they also cannot be composite, so they need to be metal. So we make ours out of steel tubes, which make up the majority of our roll cage structure. The tubes are then bent by a third-party company, and then we tack weld them, and then they're further welded by professionals for installation. And this is sort of to be like a protection mechanism in the event of a rollover accident, which we thankfully have never had to use yet on the team. Getting more into the electrical side of things, our team kind of deals with all of the like electrical components in the car. I'll go over like the battery, the motors, vehicle controller, telemetry, and there are many other like small systems that work together to make the car drive. So going over a general overview of the car, we have our 130 volt high voltage bus, our 24 volt low voltage bus, and our 125 kilobaud CAN bus. And then all the printed circuit boards that we have in our car are designed by students using Altium. Going over the battery, we assemble all of the individual cells in parallel into modules, which is done by spot welding into a nickel sheet. These modules are placed in series, and they give our car the desired voltage of about 95 volts to 150 volts. And this powers all the systems on the car. And then we also have our battery management system, which monitors the battery health and performance to give that information to all the different boards when making decisions regarding like motors or anything else that requires significant energy. So now going into the motors, this is kind of one of the parts that our team is most proud of. We're one of the few teams to design and build our own motors at the different solar challenges that we go to. So we custom design and our own permanent magnet AC motors. These typically have a top speed of about 65 miles per hour. So similar to like how a normal car would be on the road. And these are designed with the car size and the number of passengers in mind to kind of give us the right output of power for driving the car. And the next system that we'll go over is the vehicle controller, sometimes called the flight computer, which is sort of the brains of the car. So that takes in measurements from the brake and accelerator pedals. And then that kind of information is used to drive the motor controllers. And it also communicates with other systems over the CAN network. So it also controls the lights, motor controllers via the CAN network. And then it takes information from like our steering wheel, our center console, as well as our charger, just so that we can monitor all of our systems with this board. And then next we have our telemetry system, which is responsible for outputting all of the information in the car. So this logs all of our messages from the CAN bus onto a micro SD card. It also transmits the critical messages via the XB radio transceiver. And then that information is sent to the program that we run on our laptops, which monitors all the critical information from the car. And then it also does support sending data over a USB serial connection. And then we like to maximize the amount of proprietary systems on our car, but however, we do have 3 third-party systems, which are the motor controllers, our maximum power point trackers, as well as the AC to DC converters. The downsides of having third-party systems are that they're not as customizable as we would like them to be, and they're typically more expensive. However, we are currently working on developing our own maximum power point trackers. So yeah, that should be implemented in future iterations of our cars.
Yeah, so moving on to the mechanical side of things, we have 5 mechanical systems with motors, suspension, steering, speed control, and rims. So for to start with motors, as you said, we do custom design motors. So we design basically everything in the motor. So from the housing to the stator to the rotor, then the axle and the hub, all of that's designed ourselves. So we have one motor directly driving each rear wheel on the car. And then these motors also act as a structural component for the suspension. So there's no upright in the rear, it's just the motor housing taking that structural load. Then for the suspension, we have a double A-arm structure in both the front and the rear. In the front, we have a aluminum upright, and then in the rear, we have the motor acting as that structural component. And then we water jet the A-arms ourselves and then mill any dimensionally critical holes later on. For steering, we do a 3-part design. So we have the driver interface, the gearbox, and then routing. As you may have seen in some of the pictures of the cars previously, we sort of have like a pontoon style design, which means we have what we call the tunnel in between. This creates a bit of a challenge for us because we need to route that steering to both of the front wheels. So we have to go up and over that tunnel. So just a bit more challenging than maybe what we'd have to deal with some other vehicle designs. But then we use a custom gearbox design as well as a custom steering wheel. But we purchase some components such as the U-joints just because they'd be too difficult to design and manufacture ourselves. So for speed control, this is really the accelerator, brake, and then parking brake. We have 2 independent hydraulic braking systems. So this is to increase redundancy and just overall improve vehicle safety. It's also required by regulations for the American Solar Challenge. Mechanical parking brake, of course, we want to have so the car doesn't roll away while we're charging off the sun, or just have the car parked and want to leave it somewhere. And then we have custom designed pedal assemblies that have integrated pedal sensors. So these pedal sensors are then read by the vehicle controller. So on both the accelerator and the brake pedal, the sensor readings, that way the car can decide how much to accelerate. But then also when you're braking, we have regenerative braking to recover that kinetic energy from the car and put that back into the battery. So we try to do that as much as possible for efficiency. And then we have solid steel brake rotors, but we try to avoid using the mechanical brake as much as possible, since when we do that, we're just wasting that kinetic energy. So for the design and build cycle, we basically start with initial aerodynamic design. We start with some high-level concepts of what do we want the car to look like. And this is often before the regulations for the upcoming race are actually out. So we'll look at the existing regulations, but then once those new regulations out, we'll take an in-depth look at those, see what's changed, and see how our designs are going to need to change to satisfy that. And after that, we'll set requirements for ourselves for sort of what are we designing for, both aesthetically and performance-wise, what are the needs for other systems in the car. And then we'll iterate on these designs and analyze them using CFD. Once we've made some progress on the aerodynamic design, we'll start doing more mechanical and structural design. So this usually starts off by reverse engineering and understanding how the systems on the previous car worked and why design decisions were made, as well as looking at things that maybe didn't turn out as well as we would have liked, or looking at things that were maybe difficult to manufacture and install. At that point, we'll review regulations and set requirements. So this is both like how easy do we want to make it to manufacture something if something was too difficult previously or too expensive previously, as well as looking at what sort of expected load cases a component might have. And then we'll start doing those designs and use FEA to begin analyzing that. And then later on, after we've started some of that design, we will finalize the aerodynamic design. So the biggest part that involves the entire team is just selecting a body design for the car. So this is obviously something a very large aesthetic choice as well as performance and design choice. So this is really a decision that involves the entire team, and we discuss what our options are and then select an option. After we've chosen the general idea of which specific design we want, we'll iterate some more just to refine that design we chose as much as possible. And then before we finally lock that design, we'll review system needs, making sure that there's enough space for everything, making sure that all of our requirements were met. And finally, review the regulations, make sure we haven't missed anything, make sure that we're within sizing requirements and other requirements that the race might have. After this, on the mechanical and structural side, those designs will get finished up. So usually there's a fair bit of design work after the aerodynamic design is locked. There's a lot of reviewing of interactions with other systems, especially with the chassis and then other mechanical systems, and then review the regulations and come up with drawings and final manufacturing plans to make sure that we have a path forward to manufacture the car. For the build of the car, we start by building the aerodynamic shell. This is pretty time-intensive process. So we start by purchasing molds for us to do composite layups on, and we usually use primarily carbon fiber, but some fiberglass for the car as well. For the chassis, we will start by prototyping with plywood, since plywood is much less expensive than composite chassis panels. So the prototyping with the plywood allows us to find any design errors that might prevent us from actually being able to physically assemble the chassis, and also allows us to make sure that the chassis is designed to fit the shell that we actually have, because due to manufacturing issues, it's possible the aerodynamic shell is going to differ some from the original design. So at that point, those tweaks can be made before we begin manufacturing the final chassis. After that, we'll go to the roll cage, get the steel tubes bent, tack weld it, and then professionally weld it. And then after that, we'll install the mechanical systems. These systems are usually being manufactured in parallel to those previous steps, since they're not really held up by anything. So once the structure of the car is coming together, the mechanical systems can be put in place and then tested to make sure they function at a basic level. So making sure your steering works correctly, making sure your brakes work, stuff like that. And then after this, there's of course still a lot to do. There's other structural systems that need to be installed. All of the electrical systems need to be installed. And then really the last step is interior, doors, windows, and array. The interior and array specifically are pretty sensitive systems. Interior, we want it to look nice as possible. So we don't want to be doing a lot of build work after that's installed. And then the array cells are, the array is very high efficiency and not super well protected against the elements. So we want to put that onto the car as late as possible so someone doesn't toss a wrench across the array and break stuff. Yeah, so then after we've built the car, we're finally getting to the point where we can race the car. We'll do test driving, make fixes, and learn how to diagnose issues and make repairs. For the World Solar Challenge, which is usually the car we will design for first, we'll ship the car about 3 months in advance, arrive in Australia a month before the race, and then continue some test driving. And then before we're allowed to race, there's a process called screw-nearing. And screw-nearing basically is the process of them making sure that we have met all of the requirements laid out by the race regulations, and then just generally making sure the car is safe and roadworthy so that nobody gets hurt. Then of course we have the chance to race, and after race, we take a look at the car and see if there's any improvements that can be made. Oftentimes these are the electrical systems, most of the mechanical systems, just because it's a much larger undertaking to redo the mechanical systems in the car than it is to replace a single electrical system. If there's any damage to the car, that'll be fixed. And then after that first race, we'll really spend time learning how we can do things better for the next car. And then once again, we'll test drive. And then the following summer will be an American Solar Challenge in FSGP, and we'll race again. So currently, we're getting ready to race Freya in July. So we're doing some work on her. So one of the big projects we're undertaking is the battery. We actually just received the battery cells to assemble the battery pack today. So build a new pack. We're using 18650 GA cells from Panasonic this time. In the past, we've used different cells, but this is what we were luckily able to get this time. And then a big change from really what we've been doing for almost the past 10 years is making this battery pack more modular. So this is going to help us a lot with assembly and manufacturing, and just make it safer and easier to build and install. Another change we're making on Freya for this coming summer is we're changing the door beams to be carbon fiber composite instead of steel. This is mainly a weight saving effort just to reduce unnecessary weight in the car. Then finally, we're revising pretty much the entire electrical system. So one of the big motivating factors for this change is that we didn't have enough microcontrollers to make more backups of the boards that we already have designed. So we had to make new designs, but we also use that opportunity to try to make our systems more robust and use more automotive grade connectors and components. At the same time, also writing a lot of new firmware, moving from C to C++, and just overall trying to make our software more organized and reusable to make the development process easier and reduce bugs in the future.
And then we're also kind of simultaneously working on car 15 right now. So we're sort of still at the beginning of the build process, where we're kind of iterating on previous designs, previous cars that we've built, trying to, I guess, improve our chances of winning future races. So that's optimizing the performance. And then the car 15 will be racing in Bridgestone World Solar Challenge in 2023, as well as the American Solar Challenge in 2024. And the goal, both of those, is to win. So right now we're mostly working on design. So a lot of systems and components are done being designed, but we're still kind of going through some revisions on the chassis, the roll cage, the motors, battery, as well as the interior of the car. So right now, one of the main efforts that like everybody on our team is working on is the composite layups of our next car. So this is kind of the like outer shell of our next car. So it's going to be built primarily using carbon fiber and Nomex honeycomb core to give it its strength. And the rear panels will be used with fiberglass, since that's not as conductive. And this is, again, a very time-intensive process that requires many hours from everybody on the team, even if you're not on the composites and structures side of things. We're also going to be shortly designing our chassis, which is sort of the skeleton of our car. We're currently wrapping up the design work, and we're going to prototype using plywood before we do the final manufacturing. A chassis panel will be cut using a 5-axis water jet, and it's sort of like the gives the car its rigidity, as well as giving us like a place to mount all of the other mechanical and electrical systems for the next car. And on the mechanical side of things, working on manufacturing parts for the mechanical systems of the car, which is a lot of water jetting in our machine shop. We're currently looking for manufacturing sponsors to help us with this effort. And we're also continuing to work on the mechanical motor design of our next car. A couple of challenges that have mainly come with the COVID-19 pandemic is we are currently unable to use some of the resources that we previously had from some of our sponsors. And then another large challenge is the supply chain issues, which I'm sure all of you are familiar with, the microcontroller shortage or the semiconductor shortage across the world. So we've had to redesign many of our electrical systems to use different microcontrollers to combat this, which is kind of due to the long lead times in productions for our previous components. And then once again, we'd like to thank all the sponsors. Without any of these people, it would be impossible to build the car. So once again, a great big thank you to all of our sponsors. And then if you're looking for more information on how to connect with us, you could find us at umnsvp.org. You could reach out to us directly at svp@umn.edu. And then we're also on all social media networks at UMN-SVP. So yeah, thank you guys.
Wonderful. Thank you so much, Brett and Matt. I can't believe how much information you shared in 35 minutes. It was amazing. So we're going to take questions now. Brett, you want to stop your screen share so that they can see all of us? Great. And we got lots of great questions. So we're going to try to jam through as many as we can here before 1 o'clock. I'm going to try to combine as many as I can. And if you asked a question early in the presentation, and I think the students answered it as they went along, I'm going to skip yours just to make sure we get through as many as we possibly can. So one that came up in a lot of different kinds of ways in the questions was the amount of time you spend on this activity. Are you all taking classes at the same time all this is happening? What happens in the month when you have to go to Australia? Are students still in class during that time? Are they taking a leave? And are you getting any credit for any of these activities? So I'll throw that to both of you.
Yeah, so that's a really good question that we get a lot. So for the most part, students generally don't get credit for most of what they do. Sometimes people will do like a directed study and get credit, or do a project as part of like a senior design course and get credit through that. But yeah, so all of us are full-time students for the most part. Occasionally people will be doing maybe a co-op. So they'll be working full-time instead of taking classes. But yeah, everyone's full-time student. And then when we go to Australia, we all required to take some amount of classes during that semester. Oftentimes that's either a directed study or maybe a online class that is easier to fit in with traveling abroad. But usually it's not a full course load. Sometimes people also work in like a co-op nicely so that they'll do a co-op for that summer in the beginning of the fall, go to Australia for that month and a half, and then come back and continue that co-op. Yeah, that's how we do it. Some of the European teams that we compete against actually do take off like up to a year and a half of school and get stipends to work on it. So we don't do that, but some of our competition do that.
Matt, did you have anything you wanted to add, or should I ask the next one?
Yeah, I guess like yeah, all of us are full-time students. I guess like one specific example of like one system that was done for like college credit was our telemetry system was done as a project as like a directed study last semester. But yeah, I'd say most of the work is just done for the solar vehicle project.
Thank you. We also had quite a lot of questions about weight. So are there different weight specifications for the different classes of car? Or do you just have a target weight that you're shooting for, and how have you done in achieving that target? And one of the questions was related to, is there some intention paid to finding the smallest people to drive the car or sit inside the car while you're racing?
Yeah, those are good questions. So there's no weight requirements on either for either of the classes. But generally you want the car as light as possible. There's both load ratings for the tires, and then the heavier your car is, the heavier your roll cage ends up needing to be. So you know, if you let your weight get away, you just start adding more and more weight. But then for the drivers, you're not actually able to do that for weight anyway, because they actually ballast your driver to I believe it's 170 pounds. So if you weigh less than that, you have to add weight to the car, and that's to avoid that specific like little strategic decision to have someone drive who's lighter. In the past, not so much with the multi-occupant vehicles, but the single occupant vehicles, people have other teams have actually chosen generally like shorter drivers so that they can make the car more aerodynamic. In future races, that's actually changing as the regulations have changed to actually make it so that a driver who's about like, I think like 6'7" can actually fit in the car. So that really like is just to prevent like that strategy from taking place.
Great, thank you. We also have quite a few questions related to temperature inside the car. So are you using any of the energy produced by the solar arrays or the battery chargers to heat or cool? And in Australia, does it get really hot inside the car? How do you keep it comfortable for the drivers?
Yeah, so it does get very hot. In Australia, like ambient temperature can be like 110 plus. When you're driving, it's not quite as bad, especially at high speeds, because there is passive airflow. There's no active cooling, but having that like passive airflow through the ductwork definitely helps. I think the worst is actually during like scrutineering when you're sitting on like hot asphalt, not really driving. Car can get like the inside probably gets above 120 degrees Fahrenheit.
Great. And then another question we had is, have there ever been any crashes in any of the races that you've been in? I know you said you haven't ever had a rollover experience. Have you witnessed any?
So I haven't seen an accident actually happen, but during the most recent World Solar Challenge in 2019, several teams actually rolled over due to high winds. So I guess for a little context on that, the single occupant vehicles are very, very light cars. Like some of these cars weigh as much as a battery does. So only a few hundred pounds, and the winds were very strong, like 50, 60 mile per hour winds. So a couple teams actually did roll over. Luckily for us, that's not really much of a risk. We do design to keep like the center of mass as low as possible. And then just with it being a heavier car, that risk is pretty heavily reduced.
Great. What is the typical number of competitors for the races? And who are some of the competing teams? One of the questions related to expressing amazement at what you do building most of your components from scratch. And is that common among the other competitors that you're racing against?
Yeah, so the number of competitors definitely varies. The multi-occupant vehicle class is definitely smaller than the single occupant vehicle class. Just it's a much larger undertaking. Like, it's a physically larger vehicle. It requires a lot more effort. So I think in the most recent World Solar Challenge, there were, I think, 13 teams that registered, but actually only 6 of those teams even finished the first stage of the race. So it's a tough race. But then for some of our competitors, in the most recent World Solar Challenge, within the multi-occupant vehicle class, team that won was from the Eindhoven University of Technology in the Netherlands. Then 2 of the teams we actually beat were UC Berkeley and then Cambridge, which I don't know, I think that's cool bragging rights. But then there's some other good US teams that don't necessarily compete against us in the single occupant vehicle class. Stanford, Michigan, MIT also compete.
Great. And then maybe this one's for Matt, since he was talking about the sponsors at the end. What are the biggest needs for the team from industry? Money, services, material, consultations, mentoring, something else?
Probably at this point, I think materials are what we're mostly looking for. Would you say that's accurate, Brett?
Yeah, I think materials and then like manufacturing capabilities as well. Heat treating, machining would probably be like the big 2.
Great. And then we have another question related to the fact that you're all students doing this. With such high personnel turnover, typically about 4 years for an individual participant, how do you handle knowledge transfer given how much knowledge is involved?
It's tough. It's probably one of the biggest challenges we face as a team, because yeah, there's so much turnover, and most people probably aren't even here for 4 years. Like, a lot of people might join, spring of the freshman year, for all of the sophomore year, and then maybe not even stay until graduation. So realistically, a lot of people aren't even on the team for 4 years. I think one thing that actually helps a lot is like we have a lot of really supportive alumni, which is a lot different than like a business. Like, if you take a job, you don't have that previous person who did that job to talk to after they've left like the company, which is a big resource that we have. Of you can email, text, talk to whoever that person was that designed the previous system that you're working on. We also have a internal wiki, something like Wikipedia, but all solar car stuff, and we've had that going for like maybe 10-15 years. So there's a lot of documentation on that. Yeah, just I guess trying to document and then mentor and teach people would be like 2 big things.
I did notice in the chat there were quite a few former members of the team noting that what car they worked on, if they were the driver, etc. So thanks all of you for being here today and supporting the current students working on this ongoing project. Another one, kind of going back to the previous question about sponsorships, what is your annual budget? And are there particular sponsorship needs you have for Freya or Car 15 that this audience might be able to help you with?
Yeah, sure. So the exact budget number is kind of difficult to give because we do get like a significant amount of like in-kind donations, but I'd say probably around $100,000. So like the races are pretty expensive, so that's like cash, but then there's a lot of like in-kind sponsorships between materials and then manufacturing services that we also get. I think for Freya, we're not doing like a ton of manufacturing, so I think like the need is less there. But as we're building Car 15, there's a lot larger need for, we're looking for machine shops to help us manufacture some of these components. As either as a sponsorship, which would be ideal, or even just a company willing to do it. Many machine shops are like heavily backlogged right now. So it's difficult to find a place that you could even pay to do stuff for. And then we're also looking for a heat treater that would be able to help us with some stuff on the roll cage.
Speaking of the roll cage, we did have a few questions related to that, why it's made out of steel instead of something lighter, and why the rules prevent you from using something like carbon fiber.
Yeah, so The rule around not having a carbon fiber roll cage is a specific American Solar Challenge rule. It makes us a bit less competitive at the World Solar Challenge, just because it's really difficult to change the roll cage once you've built the car. The reasoning, I think, is largely just they don't trust students to build a sound composite roll cage. You have to have a lot of technical knowledge, probably technical knowledge that we barely have. And I'd say we're one of the better, more experienced teams. So that's really the reasoning there. And then for choice of metal, realistically, like other choices aren't going to necessarily lighten the roll cage that much, even if like the metal itself is lighter, just because of how strong the roll cage actually needs to be. Like aluminum, for example, probably wouldn't actually be suitable. And then other metals like become much more expensive. So we have to balance like cost and performance on that aspect.
Obviously, you've had a lot of success over the years. And what do you both attribute to being what's most responsible for your success? Do you think it's the design of your car, the execution of construction, your team tactics, or some of the ways that you approach your race day and how you might drive the car? Is the driver you select making a big difference in how you perform in the races? What do you think leads most to the success that you find?
I think a big factor is just the pure amount of time like people put in. I think like historically the team has been heavily dedicated to the project, and people have just been really motivated to put in the work. And then I think I guess specifically like on our races, not just like building a good car, but we do a really good job compared to other teams of just training and preparing. And when we go to the race, even like this past summer, as we were like finishing the car, like coming out of COVID is very hectic. Didn't prepare as much as we would have liked. We were still by far probably the most prepared team there. Just that like being prepared, knowing what you need to do makes a huge difference, and it helps you like avoid unforced errors and making mistakes that you don't need to make.
Yeah, I'd say like the dedication of all the individual team members is definitely a huge factor that contributes to just how much work that we can get done in the time that we have. And then I guess yeah, we do have a lot of like Brett mentioned earlier, like a lot of alumni who kind of passed on a lot of knowledge to us. So we have kind of a big collective body of knowledge to base all of our decisions off of. So that always helps.
Do also see a couple of questions about the sort of design change with some of the newer vehicles with the kind of tunnel shape underneath and what the purpose of that is.
Yeah, so that's really to reduce the aerodynamic area of the car. So in addition to like the drag coefficient, like the frontal surface area is the other big factor. So if you just cut out a piece of the car, you can make it more aerodynamic. There's designs we could choose that we could probably achieve similar aerodynamic characteristics, but just that's sort of what we've been doing. So maybe in a future car, we might not do that.
Another couple questions about the solar arrays. Do you use any special coatings on those? I guess what are they comprised of?
Yeah, so we in the past have gotten different lamination materials from 3M, encapsulation materials, and those improve the amount of light that even if it gets reflected off those cells will actually get reflected back at them. So that helps improve efficiency. And some of those materials will also help improve the angle at which the light coming in will actually hit the cells. So that's like one way we improve efficiency using materials.
Right, I'm going to try to get us through two more questions. I see we're getting pretty low on time. There were a couple questions about the interior. How do you design that? What materials do you use? Is that part of the scoring, like how comfortable and aesthetically pleasing the interior is?
Yeah, so that's part of that practicality scoring. So that's actually a large part of the score. So we do want to make it comfortable for people to sit in, make it look nice. Usually, like in addition to like some more objective categories, there's also a category for the judges to sort of just like give points to like the car they just sit in and feel like is like the better car, even if it doesn't necessarily have specific objective thing that makes it better.
Okay, and we'll make this our last question. How do you publicize your activities? If people on this call want to stay up to date with you and follow your activities, what should they do?
Yeah, definitely follow us on social media. We're pretty active on Facebook. You should be able to find us at University of Minnesota Solar Vehicle Projects, or Instagram and Twitter. We're also pretty active at UMN SVP. And we do also have a website where you could probably reach out to us directly, umnsvp.org.
Great, thank you so much. I guess I'll just give you each one more opportunity to say, is there a thing that you think in all your time and experience on the solar vehicle project, what's the thing that you think you'll take away the most, or that's been the most meaningful experience for you?
That's a tough question. I mean, I think just like the personal and professional relationships I've built have probably been most valuable. Like I've gained a huge amount of technical skills, but I think just like getting to know all the people I have has been really great.
Yeah, I'd say definitely just like this. It's like the type of learning that you don't really like get in a classroom. It's I don't know, very like the way that like we kind of do things is very professional, like dealing with like sponsors, all that stuff. Yeah, it's kind of just getting to work with that like kind of same group of people for like a kind of a project that we're all passionate about is kind of a great like experience for me as well.
Wonderful. Thank you both for sharing. We're out of time. I think we got through a ton of questions, but I think it was only about half of the ones that got asked. So thank you all for being such an engaged audience. I think we could have easily spent another half an hour. We really appreciate your attention today and your excitement and interest in the group and the students and what they're doing. I'm going to close us out with just a couple of quick announcements. And first, as a reminder, we are recording this presentation and we will share the link to the recording with everyone who registered. And you're free to share it around if you think there's other folks who might enjoy watching it. Usually takes us about a week to get the captions ready and get that out to you. So watch for that, and we'll put all the links that the students mentioned to their social media accounts and website and so forth in that follow-up email for you as well. I'd like to briefly mention the next CSC event coming up. It's for alumni, donors, friends. It's a public lecture. All are welcome. It will be in person, so we're going to dip our toe back into that. And it's the next installment of the college's Rising to the Moment lecture series. It will be presented by Dr. Jayshree Seth, who is the Chief Science Advocate at 3M. And she's going to be talking about a wide variety of things, but one of which will be the importance of diversity in STEM and how that impacts the public perception of science, which is a thing that she's really focused on as the Chief Science Advocate for 3M. That event's coming up on Tuesday, April 12th at 6:30 p.m. in Kaufman Union Theater. And you can read the full description of the talk as well as register for the event at csc.umn.edu/public lecture. It's free, all are welcome. And finally, there's always a lot of other upcoming events at the college, and you can see the full list at csc.umn.edu/events. And for questions, you can contact me at cscalumni@umn.edu. So a final huge thanks to Brett and Matt for sharing so much information with us today. It's really inspiring to see what our students are able to do while also taking a full course load. I think you're a really great example of what the scientists and engineers of tomorrow are doing today to get hands-on experience. So thank you so much for making the time to be here today. And thank you to all of you for tuning in and attending and for all of your great questions and attention. Thanks so much. Have a great afternoon.